kids! How are you? It's me again, Teacher Carly. And now, we will go and diverge into another world of beautiful things here on Earth. And our topic for today will be all about geology. And I'm sure that you are pretty excited to discover a lot of things that is secretly found actually in the core of the Earth. So I want you to listen carefully and enjoy watching while I will view you the next video. So enjoy, sit back, and get your popcorn. Come on, let's go!
To start us off with, the word geology comes from the Greek for geo, meaning earth, and ology, meaning the study of. Geology involves studying the materials that make up the earth, the features, for example, and the structures that are found on earth, as well as the processes that shape them. Geology can also refer to the solid features of any celestial bodies. Celestial bodies being asteroids, planets, or comets. Geology also studies the history of all life that's ever lived or is still living on our Earth today. Studying how life on our planet has changed over time is an important part of geology. Geology can be incredibly varied, and people study all sorts of different things. For example, natural hazards like volcanoes and earthquakes. The inside of the Earth is made from a core, a mantle, and the overlying crust. There's also fossils, resources, including oil and gas exploration, and also looking for precious metals. And finally, for space exploration, for example, studying Mars or the Moon. So that was geology.
Dr. Binox! Dr. Binox? Oh, hello friends! The best part of a pizza is its crust. Yummy! Just like this pizza, the Earth too has a crust, but with no cheese in it. So, let's learn something about the structure of the Earth today. It consists of the crust, mantle, and core. Zoom in! This is the Earth's crust. It consists of all kinds of rocks, soil, and everything you see above the Earth's surface. You will be surprised to know that the crust, that is the land on which we walk, is almost 3 times thicker than the crust under the oceans. And it extends to about 25 miles. The Earth's crust floats on this layer, which is called the mantle. It is made of thick, solid, rocky substance and amounts to about 85% of the total mass of Earth. The first 50 miles of the mantle consists of very hard, rigid rocks. The next 150 miles are made up of super hot, solid rocks. Below that, for the next several hundred miles, the Earth's mantle is believed to be made up of very solid and sturdy rock materials. The mantle is about 1,800 miles thick and by far the largest layer of Earth. The Earth's outer core is made up of super hot liquid molten substance called lava. This lava is believed to be made of iron and nickel. It extends to a depth of 3,000 miles beneath the Earth's surface. And finally, we have reached Earth's inner core. The inner core extends another 900 miles towards the center of the Earth. It is believed that this inner core is a solid ball made of iron and nickel. Trivia time! The crust occupies less than 1% of Earth's volume. The inner core is the hottest part of the Earth, and it is as hot as the surface of the sun. Surprising, isn't it? Looks like it's time for me to zoom out before I get baked in this heat. You know what, guys? I just love rock music. But we thought you love only one kind of rock. The original ones. Us.
That's right. Weren't you supposed to tell your friends about us?
Whoops. You're right. I think I should take some break from rock music and tell you guys about the different types of rocks. Happy now? Woo! Finally! Come on, guys. We got a lot to learn about different types of rocks. Zoom in! There are three major types of rocks based on their formation, and they are igneous rocks, sedimentary rocks, and metamorphic rocks. Igneous rocks. The name igneous is derived from the Latin word ignis, which means fire. So igneous rocks are formed when the molten matter inside the earth, called magma, comes out of a volcano and later cools down and solidifies. There are two types of igneous rocks. When the magma cools down and solidifies inside the Earth's surface, they are known as intrusive igneous rocks. When the magma erupts above the Earth's surface and solidifies, extrusive igneous rocks are formed. Pumice and granite are some examples of igneous rocks. Sedimentary rocks. Sedimentary rocks, as the name suggests, are comprised of sediments. These sediments could be minerals, small pieces of plants, and other organic matter that have been compressed and deposited over a long time. These rocks can be generally found on ocean and lake beds and on rocky surfaces on the Earth's crust. Sandstone and coal are some of the sedimentary rocks. Metamorphic rocks. When the igneous and sedimentary rocks are exposed to high temperatures and pressures, they undergo change. And this process of changing from one form of rock to another is called metamorphism. But hey, that takes a really long time, maybe thousands of years. However, this process doesn't melt the rocks, but instead transforms them into denser, more compact rocks. Slate and marble are some examples of the metamorphic rocks. Trivia time! The upper segment of the Earth's crust is made up of about 95% of igneous rocks. The Taj Mahal in India is completely made of different types of marble, a metamorphic rock. See, I told them all about you. Doesn't that make you happy?
Yeah, very happy. Whee!
So, this is me zooming out. Tune in next time for
The idea that our planet's continents drift around the globe, periodically glomming together and breaking apart, is at least 200 years old. But most geologists didn't believe it until the 1960s, when mounting evidence made it clear that the Earth's crust is broken up into fragments, and that those fragments, called tectonic plates, are moving. And these days we directly track that motion, with millimeter precision, from space. The common simplified explanation for why tectonic plates are moving is that they're carried along on currents in the upper mantle, the slowly flowing layer of rock just below Earth's crust. Converging currents drive plates into each other, diverging currents pull them apart. This is mostly true. Hot mantle rock rises from the core and moves along under the crust until it grows cool and heavy and sinks back down again. But the plates aren't just passively riding these currents around like a bunch of suitcases at the baggage claim. They can't be, because some of the plates are moving faster than the currents underneath them. For example, the Nazca Plate, a chunk of ocean crust off the west coast of South America, is cruising eastward at about 10 centimeters per year, while the mantle underneath it oozes along at just 5. Neither tectonic plates nor luggage can move faster than the belts they're riding on unless something else is helping to push or pull them along. And some of Earth's plates, it turns out, are pulling themselves. When an ocean plate collides with another ocean plate, or a plate bearing the thick crust of continental land masses, the thinner of the two plates bends and slides under the other. As the edge of the sea floor sinks into the mantle, it pulls on the plate behind it, the same way a chain dangling further and further off a table will eventually start to slide. The bigger the sunken portion of the plate becomes, the harder it pulls and the faster the remaining plate behind it moves. You can find where this is happening just by looking at Google Earth. The incredibly deep, narrow ocean trenches visible off the coasts of some continents and island chains mark the creases formed as ocean crust plunges downward, bending the edge of its neighbor in the process. What's more, these chunks of seafloor are actually helping to drive convection in the mantle beneath them. Sunken slabs of ocean crust block flowing rock from moving further sideways, forcing it to turn downwards and sink. And eventually those slabs get too heavy and break off, plunging slowly toward the core and creating a suction force that pulls mantle material along behind them. So in some ways, seafloor crust is really more like part of the conveyor belt than something riding on top of it. The continents, on the other hand, are baggage.
What is geomorphology? It is the branch of physical features of the surface of the Earth and their relation to its geological structure. It's a scientific study. Many scientists work hard to develop science. Some famous are Herodotus, a work of history that would contain a wealth of geography, description covering much of the known world. He's the first who noted the process of large rivers. Aristotle, he was a famous person in geography. He was a philosopher. He noted that the Earth's shadow during an eclipse is curved. Strabo, he observed the sinking and rise of land, value of temperature as a result of earthquake. His volume series called Geographia, in which he described Davis' geomorphic cycle. Davis stated that geomorphic processes without further complication from tectonic movement then gradually wear down the rock topography. Types of geomorphology: physical, chemical, and biological geomorphology. Geomorphic processes: erosion, transportation, and deposition. Erosion, detachment and removal of rocks. Transportation, the movement of material across. Deposition is a geologic process in which sediment, soil, and rocks are added to a landform or land mass.
The Earth is a complex system of parts. But what are the parts and how do they interact? Is a group of individual parts or events that interact to form a complex whole. The Earth is one of the most complex systems we know about, with an enormous amount of processes that shape the Earth to how it is now. We still have yet to know many of the cogs in the giant clockwork of our world. Processes are interactions inside or between the four spheres of the Earth system. The atmosphere is our special mix of gases that surround Earth. They can affect everything from temperature to the wind. The hydrosphere includes all of the water on Earth, from the water frozen at the poles to the water that comes out of your tap. The geosphere is the physical sphere of Earth. It includes all of the mountains on Earth's surface and describes how rocks and minerals interact. Finally, the biosphere is all living things on Earth, from plants to bacteria. Even you are part of the biosphere. These four spheres, the atmosphere, hydrosphere, geosphere, and biosphere, interact to form the complex processes of Earth. These four spheres can interact in many ways and explain many natural phenomena. The interaction between spheres you are probably most familiar with is the water cycle. Water can evaporate from a body of water into the atmosphere. Once there, it may become part of a cloud and rain over land. This rain may become groundwater, or part of an underground pocket of water. Eventually, that drop of water may be consumed by an animal or plant, making its way into the biosphere. Of course, this is only one example. Global warming is caused by an interaction between the atmosphere, geosphere, and hydrosphere. Even the formation of hurricanes is due to an interaction between the hydrosphere and atmosphere.
Geological time scale. Scientists have divided the Earth's history into different categories of varying size. They go as follows. Eons can be divided into eras, which are divided into periods. First and foremost are the eons. These are the longest divisions of Earth's history. They divide the last 4.6 billion years of Earth's history into four sections. The Hadean, where the molten Earth was bombarded by meteors, was the first eon. Next was the Archean, when the oceans had formed and life spread. The third eon was the Proterozoic, which saw the evolution of eukaryotic and later multicellular cell. Next was the Panerozoic eon. It is divided into three eras, the next division in the geological time scale. The three eras of the Panerozoic are Paleozoic, Mesozoic, and Cenozoic. The first era, the Paleozoic, is divided into 6 periods: the Cambrian period, the Ordovician period, the Silurian period, the Devonian period, the Carboniferous period, and finally the Permian period. The next era, the Mesozoic, was divided into 3 periods: the Triassic period, the Jurassic period, and the Cretaceous period. The era we are currently living in, the Cenozoic era, so far as three periods, the Paleogene, the Neogene, and the Quaternary, which covers the last 2.5 or so million years. As you can see, all the periods we discussed take up less than 12% of the history of the Earth. Within this 12% is where most of the meat of prehistory lies: human ancestors, the age of dinosaurs, giant insects, and evolution. The first three eons we talk about at the beginning of this video are sometimes collectively called the Precambrian Superion. As you can see, the Precambrian takes up most of Earth's history, even though important evolutionary events during this time are few and far between.
Paleontology is the study of fossils and the history of life. It is the discovery of new kinds of life. This tells us who we are and how we came to be. People who study fossils and the history of life are called paleontologists. Most of the time, paleontologists have been interested in ancient creatures like dinosaurs from the time they were very young. They go to school for many, many years to study the Earth's history. They have to study geology, chemistry, biology, and astronomy. They have to know about volcanoes, the rocks around fossils, and what these fossils are made of. They need to know how creatures work on the inside, and they need to know what happens in outer space. Paleontology has three basic goals. The first is to describe different kinds of creatures that lived on the Earth many, many years ago. This means studying, drawing pictures, and taking photographs of fossils, and often rebuilding ancient creatures for others to understand. The second goal is to create a more complete story of life on Earth. And finally, a third goal is to develop new ideas about evolution and other scientific theories. Being a paleontologist isn't always easy. Sometimes, a paleontologist will turn over a stone and find an incredible skeleton of an ancient creature. But this is very rare. Most of the time, digs for dinosaur bones take many, many years. They are done slowly, 1 square foot at a time. Paleontologists have to be ready for change all the time. Our ideas about the history of life on Earth are always evolving. We are finding more and more fossils that tell us new things. Our tools are becoming better and better. New discoveries can change what everyone used to think was true. The study of paleontology means that you are always going back and questioning your beliefs. But paleontology isn't only about history. It's also very important for our future. We can learn how the Earth is changing, how the climate is changing, and how we, human beings, have made changes to this planet.
My name is Bruce Dale. I'm the Chief Subsurface Engineer with ExxonMobil. My job really entails one of supporting the management and the technical staff in some of the upstream challenges that we have in the industry. Spans everything from exploration to development, drilling, production, and then eventually abandoning. It goes actually back to the very early days of Abacus when it was virtually a startup company. And ExxonMobil was one of the first licensees, and in fact it was the first licensee in the energy sector to use the product. And I described a number of years ago at one of the SCCs about 3 decades worth of applications that ExxonMobil has had in using Abacus for solving a variety of upstream problems. Because many times there's not opportunity to experiment, so time scale would not fit within the period in which a decision needed to be made. But with simulation, the opportunity exists to be able to impact the here and now, much more so than was ever available before. Of course, in the early days, the way that we analyzed the results of simulation was more tabular in form, and visualization really hadn't come into its own. Of course, today, with modern computers and the like, visualization is part and parcel with the simulation itself. Allows you to do the interpretation, be able to spot opportunities or flaws much earlier than historically we would have been able to have done. So within the upstream oil and gas business, visualization is a great aid in the being able to bring folks together to, of desperate types of information analyses and data to be able to solve some very tough problems.
Astrogeology. The science dealing with the structure and composition of planets and other bodies in the solar system.
Yes, kids, that's all the topic of geology. But the most important thing for us to continue the study of geology is to give importance to it and to take care of our Mother Earth. And the next video clip will be our own little ways on how to take care of our Mother Earth in order for us to continue studying and living here on Earth. So please watch. Thank you.
Taking Care of the Earth by ESLKidsWorld.com. My name is Terry. I am a student. I live here on planet Earth. I love the Earth, and I bet you do too. The Earth is a beautiful place to live. Unfortunately, people don't always take good care of our Earth. People hurt the Earth by cutting down trees, polluting waterways, and wasting electricity. Our planet Earth needs to be protected. Otherwise, everything from the water we drink to the air we breathe will be affected. We can protect the Earth by reducing, reusing, and recycling the items we consume. We can protect the Earth by cleaning up litter. We can protect the Earth by saving electricity. We can protect the Earth by conserving water. We can protect the Earth by planting trees and reforesting woodlands. We can protect the Earth by reducing the use of single-use plastic. We can protect the Earth by riding bicycles instead of driving vehicles. We can protect the Earth by composting food waste. There are a lot of ways to take care of the Earth. Our care can make a big difference. Let's make every day an Earth Day. What can you do to protect the Earth?
That's all, kids, and I hope you learned something new today. So enjoy in your new adventures in life. Until next time, bye-bye!